The next characteristic of light we're going to talk about, well, it's not unique to light, but we're going to talk to it as applied to light, is reflection. All waves will reflect to some extent when they hit a boundary. It doesn't matter what type of wave it is. It doesn't have to be just light. Sound, for example, reflection with sound is your echo. Our interference before, when we talked about standing waves, for example, it was the wave and its reflection that were interacting with each other. So reflection is not unique to light, but we're going to talk about its application with light. We have the law of reflection, which you probably already know. If you have a nice smooth surface, if you have a wave that comes in, it's going to bounce off at exactly the same angle it came in at. We measure our angles relative to the normal. So if you draw a normal line, the line perpendicular to the surface, the angle in, so we call that the incident angle, is the same as the angle reflected. So theta incident is equal to theta reflected off a nice smooth surface. So the same angle it goes out at as it came in at. Now with light itself, it is a transverse wave. I'm not going to draw it as a transverse wave on the board. To represent light, I'm going to use just what we call a light ray. Just going to use an arrow to represent some section of the light that's traveling in that specific direction. Now realistically, we have a ton of light everywhere reflecting off of everything. We're only going to draw a couple light rays as we look at our problems, as we go through our different concepts. So the arrows just represent the direction the light's coming from, and then that arrow coming back off is the direction the light continues after it reflects. So mirrors, obvious example of reflection. You're all familiar with mirrors. I'm sure you look in one at least once a day.
Capture my soul. It's a camera.
Yeah, high tech. So we have, this is a flat mirror. That's what you have in your bathroom. Images. Okay. Image is what we're seeing in the mirror. You see yourself in the mirror. You see other things around you in the mirror. Whatever you're seeing in there is the image. Whatever was the original you, for example, out here, we call the object. So the original object, the original entity that we're looking at its image in the mirror is the object. With a flat mirror, let's say we're standing in front of a flat mirror. So here's the mirror. Draw those lines just to represent that's the back side of the mirror. When we talk about mirrors, and this will apply to lenses as well, one piece of information that's useful to us is how far away the original object is from the mirror. We call it the object distance. It's measured from the original object to the mirror itself. Our book uses the letter S to represent it. So S being a distance from the mirror, from the object to the mirror. With a flat mirror, the image shows up back here. When you look in this mirror, your image appears to be back behind it. So further behind the mirror than what you're at. What we're seeing is due to reflection. For example, we have light from our feet that hits the mirror, reflects off, and hits our eyes. Okay? Now there's a whole bunch of light from our feet going everywhere. The only one we're seeing is the one that hits our eyes. We have light from our hands reflecting off the mirror and hitting our eyes. what we're seeing, if we project this reflected light ray backwards behind the mirror, that's where we see our feet. That projected light ray backwards is where our feet will appear in the image. If we project this reflected light ray backwards, that will be our hands. Similarly, if we drew some light rays from our head and projected the light ray backwards, we would have the location of our head. Now, the light itself does not physically pass through the mirror. It doesn't go through and actually go behind the mirror. We call this an image. This is our image. The distance from the mirror to where this image is located is called the image distance. Your book uses an S prime to represent that. Now, prime in physics doesn't mean take the derivative. So you're not taking the derivative of anything there. S prime just means another S value. Turns out, this particular type of image is called a virtual image. Reason why? Imagine. You see yourself behind the mirror. Do you think we could run behind this mirror, set up a movie screen, and see your image on the movie screen? No. None of that light is passing through the mirror. Okay? This image isn't physically there. There's no physical light that goes back there. We see the image just fine. But for the fact that the light doesn't physically travel back here, that's what makes it a virtual image. Okay?
So no more barking at mirrors for me.
No more barking at mirrors?
Yeah. My son loves the mirror.
Most kids love to see themselves in mirrors, yeah. Now, mathematical concepts, just an FYI. To represent a virtual image mathematically, you will always get a negative S prime value. So when you solve things out mathematically and you get an answer for S prime, it will be negative. A negative value of S prime means it's a virtual image specifically. And it means for mirrors that it is behind the mirror. Okay?
Or for a flat mirror.
No, it's for any mirror.
Sorry.
Yeah. S prime being negative is always going to be behind on the mirrors. So for mirrors, the virtual image is always behind the mirror. Okay. Now we have a nice couple of equations that relates S and S prime together. One of them is this. 1 over S plus 1 over S prime is equal to 1 over F. F is called the focal length. F is where, if you have light coming from far, far away, hitting your mirror, it's where that mirror would focus the light. Okay? It's related to how curved the mirror happens to be. It is actually equal to exactly half the radius of curvature of the mirror. Now, it's a little screwy with flat mirrors. To figure out and think about radius. I want you to imagine this mirror is part of a sphere. How big would the sphere need to be for a side of it to actually look straight? Infinitely huge, exactly right. Really, really big. For a flat mirror, R is infinitely large, which means the focal length is also infinitely large. If we put infinity in for F, the focal length, what's 1 over infinity?
0.
0. This side goes to 0, we get 1 over s, taking this to the other side is equal to negative 1 over s prime. Let's cross multiply, we'll get s prime is equal to negative s. Now this is specific for a flat mirror. What that tells us is that the image distance, negative means it's behind the mirror, means it's virtual, but it's the same magnitude as the object distance. With the flat mirror, your image looks to be the same distance behind the mirror as you are in front of the mirror. Okay, that's what we get for flat mirrors.
You were saying the virtual image is the negative s prime.
Yes.
Do we automatically just assume that whatever number goes in for s prime is going to be a negative?
If we were working backwards to find s, then yeah, you would put a negative value on it.
Okay.
But if you were solving for s prime, your algebra needs to work out and give you a negative answer.
So those two negatives will cancel each other.
Well, no. If you were solving for s prime, you would not put you wouldn't put anything else in for s prime because you're solving for it. Your algebra would have to work out to give you a negative answer. If you don't get a negative answer for s prime, then you've done something wrong. Okay.
I think the question is, if the actual s prime is negative, then you put that in there and you get negative times the negative s prime. I think that's what.
Well, I know, but that's what I'm trying to say, is if you are putting a value in for s prime to solve for something else, then yes, you have to put the negative value on it. If you are solving for s prime from the equation, then you should come up with a negative answer. You're not putting anything in for s prime. And you can't just tag a negative sign on it because you want to. The algebra itself, if you're solving for s prime, the algebra itself must give you a negative answer. Okay? Does that make sense? We'll do some examples, so you'll be able to see. So this equation we'll use a lot. It actually works for all of the mirrors we're going to look at. Now, this side doesn't always go to 0. This side only goes to 0 for a flat mirror. The other equation we have is for the magnification. How big the image is going to be relative to the object. We actually have a couple of equations. Magnification is equal to negative s prime over s. That's one equation. Turns out there's a couple of meanings in here that we get from this. If magnification ends up being positive, which it would in the case of a flat mirror, in place of s prime here, we know s prime is equal to negative s. So if we put a negative s in here, the negative signs are going to cancel. S over s is 1. For a flat mirror, magnification is positive 1. Okay? The sign and the number mean different things. Okay? Positive 1 would be different than negative 1. If your magnification is positive, that means your image is upright. If your head's on top as the object, then your head's on top in the mirror. That's what it means to be upright. Okay. If your magnification is negative, then your image is inverted. Meaning, if your head's on top, normally, when you look in the mirror, your head's going to be on the bottom. You're going to be upside down. You're also going to be backwards. Okay, so if you were to wave your right hand, the left hand in the image would wave back.
Is that like the reflection you get from the spoon?
Yeah. Yeah, so if you're looking into the spoon itself, you can see yourself upside down. You're inverted. Okay. The positive and negative signs are these are the results regardless of what the numerical value is. Okay? The number could be positive 30 or negative 30. The positive would mean it's upright, the negative would mean it's inverted. The numerical value, the magnitude of the magnification. If you're bigger than 1, if the numerical value, regardless of whether it's positive or negative, if the numerical value is bigger than 1, your image is bigger than the object. If it's less than 1, then your image is smaller than the object. Now, of course, it can also be equal to 1, which it is for a flat mirror. If it's equal to 1, then it's the same size. So the object and the image are the same size. So they have the same height, same width, all that good stuff. Now, the only inversion that happens with all mirrors, even a flat mirror, when we say it's upright, we mean the head's still on top. All mirrors invert front to back. That means whatever's on front in the object is in front when you look at the image in the mirror. Whatever's on back is in back on the image in the mirror.
To look in the mirror and see your back.
Exactly. If the mirror did not invert front to back, you would look in the mirror and see your backside the whole time. Which, yes, would be a little odd. So all mirrors invert front to back. When we talk about upright and inverted here, it has to do with actual vertical orientation. So upright means if I'm standing with my feet on the floor and my head up above, the image has feet on the floor and head up above. Inverted means, boom, it's upside down. So now the floor's on top and the ceiling's on the bottom. Okay. There is one more relationship for magnification. The magnitude of the magnification can be found by taking the height of the image over the height of the object. So h prime meaning how tall the image is, h being how tall the object is. So you can always find the magnification if you know how tall both the object and image are. The sign, though, you'll have to figure out on your own. But it turns out, for example, a flat mirror, we know the sign. The sign is going to be positive because the flat mirror always gives us an upright image.
How do you measure the height? I guess you'd have to project an image of a ruler. You'd have to stand next to a ruler and see what it is.
Exactly. So you'd have, for like a flat mirror, you'd have to have someone kind of holding a ruler up for you so you can kind of guesstimate how tall it is. There are some mirrors that give us real images, so we could actually physically project it onto a screen, and you could just measure it on the screen. So you'd have to have some sort of ruler.
Yeah, I just got a little confused. We were talking about how all mirrors invert everything.
They invert front to back.
But on the positive upright, does the inverted mean upside down? Then
Yes.
You're saying that.
This inversion means upside down and backwards. Okay. So we kind of just take it for granted that all mirrors invert front to back. And just leave it at that. Once we talk about inversion now, it's only going to mean upside down and backwards. Okay. So flat mirrors, the radius of curvature is infinitely large, which makes the focal point infinitely large, which means S prime is going to always equal negative S for a flat mirror. That gives us a magnification of positive 1. Positive means it's upright. 1 means it's the same size as the object. Okay? Those aren't the only type of mirrors we have, though.